In our previous lectures, we have been talking about in Chapter 2 now, the measurement in chemistry, the mole, molar mass. We talked about how we can determine percent composition. Yesterday we even looked at then how we can use percent composition to determine an empirical formula. Today we're going to go back and look again a little bit at how we can apply this concept of the mole and its relationship to mass. We're also going to take a look at a couple more empirical formula calculations, and we'll go on to look at what we call the molecular formula. So we'll start today then by taking a look at problem number 9 at the end of the chapter, 9 part C. It asks us to calculate the number of chlorine atoms in 12.6 grams of the compound CCl2F2. Chemical name of that compound is dichloro-difluoromethane. You don't need to remember that, but it's a chemical that we call Freon. It is the refrigerant that is used, that has been commercially used for many years. Freon, dichloro-difluoromethane. It tells us that we have a molar weight, or a formula weight, of 120.91 grams. So we already have that piece of information. Now let's also remember what else we know about then materials. We know that 1 mole of CCl2F2 would have 6.02 times 10 to the 23rd molecules of that substance, Avogadro's number. In addition to that, we also know from the chemical formula that there are 2 chlorine atoms in each molecule. So we have 3 things then that we can state relative to this problem. We know its formula mass. It's calculated and given to us in the problem. We know that a mole of the substance has that number of molecules, and we know how many atoms of chlorine there are in a molecule. So we will have 3 conversion factors that we will be using to change from grams of this compound to atoms of chlorine, as the problem indicates. So setting the problem up then, and what I'm going to do here, because we'll need a little bit more space, I'm going to use another transparency here and just set it sideways so I have a little bit more room to write across. All right, so what we want here are chlorine atoms. Now, let me point out that I'm going to set the problem up in one continuous setup. You can take each individual step as a separate math calculation and then carry the information that you've just calculated into the second step or the third step or the fourth step, whatever number of steps necessary. So you don't have to set it all up in one continuous long equation. If you prefer, you can certainly do it piecemeal instead. I'll set it up this way first of all. Chlorine atoms then are equal to 12.6 grams of CCl2F2 multiplied by 1 mole of CCl2F2 per 120.91 grams. Now at this point we will have eliminated then grams from our problem. We have the number of moles. The number of moles is sort of going to be central to all of our problem solving, or certainly to a majority of our problem solving in chemistry. Quite frequently, one of the first things we're going to ask in any problem relating how many moles Do we need to find the number of moles? Will finding the number of moles help us solve the problem? And in most cases, it will. And so that's sort of the central part of our problem. Now, we want to change from moles to molecules. And we have Avogadro's number to use to do that. And so now we can multiply by 6.023 times 10 to the 23rd molecules. I'm still going to run out of space, per 1 mole of CCl2F2. And now the moles will cancel. But I'm still not at atoms. And so the next step would be to put in a conversion factor that would convert from molecules of CCl2 to atoms of chlorine. Well, I guess what I'll do is I'll do it this way for this time. We're going to multiply now by 2 chlorine atoms per 1 CCl2F2 molecule. And so the molecule will cancel, and our final unit left in the problem is chlorine atoms. Now, obviously some of it's already off the page over there, so we can't see it all, but we do have then the 3 steps, and our units that we finally have, chlorine atoms, is in fact what we ask for in the problem. Now we would do the mathematical steps then to get us to a numeric answer. And I'll slide this back just a little bit so we can at least see the numbers that we're going to involve in our calculation. So we're going to have then 12.6 grams multiplied by 6.023 exponential 23. Remember, don't hit the times and 10 in there, just exponential 23. Then, as I suggested yesterday, so that no matter which way you proceed on the calculator, in between each math step, if you hit the equal sign, you can't make an error in terms of the logic you put into the calculator. So I'm going to hit equals now, and then I'm going to hit multiplied by 2, and I'm going to hit the equal, and I'm now going to hit divided by 120.91 and equal again, and I've now put in all of the numeric values, and I have a final answer then of 1.2. Now looking at our numbers here, we have only 3 significant figures here, 5, 4, and unlimited. I mean, there are exactly 2 chlorine atoms per molecule. There can't be any fractional amount. So that's an exact number. So we're limited to 3 significant figures, which gives us then a final answer of 1.26 times 10 to the 23rd chlorine atoms. Okay? Now, as I said, that's one way you can proceed. Set it all up in a problem if you have room on paper and feel comfortable to do that. That's certainly a logical way to proceed. However, also, as I said, you could set the problem up in 3 individual steps. Let me just quickly go ahead. We won't do the math part, but let's look at how we could proceed. The first question I would ask, based on the information we have, is how many moles of CCl2F2 I have. And if I did that, I would say, all right, we have 12.6 grams of CCl2F2 multiplied by 1 mole of CCl2F2 per 120.91 grams of the compound. Now, at this point then, I would mathematically calculate the number of moles of CCl2. My next step would be to ask the question, well, now that I know how many moles, how many molecules do I have? And so I would now set up the next part of the problem. I would say molecules of CCl2F2 would be equal to the number of moles, which we just calculated, multiplied times 6.023 times 10 to the 23rd molecules, again I'm running out of space here, per 1 mole. And so our unit moles would cancel. Calculated now, we'd have the number of molecules, and then I know that the question is number of atoms. I would add then a final step, chlorine atoms would be equal to the number of molecules that we just calculated, multiplied by 2 chlorine atoms per 1 molecule. So we can then set it up in individual steps. And if this seems easier to you than trying to put continuous cancellation conversion units, certainly feel free to do so. There is no just one correct way to do a problem. You have to decide what makes sense to you, the easiest approach for you, and that's the way you then proceed. The next problem I want to look at takes us back to what we were talking about in the previous lecture on calculating empirical formulas. Remember that an empirical formula is the smallest whole number, and that's critical, whole number ratio of atoms in a chemical compound. If we have either mass information or percent information given to us, we can proceed. It doesn't have to be in percent, it doesn't have to be in mass, it can be in either. Of course, all of the elements have to be expressed in the same manner. The example we did in the previous lecture, the information was given to us in the number of grams of each of the elements. This example gives us the information for the elements in terms of percent. But you see, if I were to take a 100-gram sample of this compound, I would have then 42.9 grams of zinc, I would have 20.3 grams of phosphorus, and I would have 36.8 grams of oxygen. I could take any size sample that I wanted to. And so whether it's in percent or mass, we proceed exactly the same way. The first step is to change from a mass ratio, which is what this is, that's percent in mass, to a mole ratio. And so what we're going to do is we're going to calculate the number of moles of each of these elements. So moles of zinc will be equal to 42.9, and we'll make it grams now. We'll take a 100-gram sample times 1 mole of zinc per. All right, remember a mole of an element is equal to its atomic mass expressed in grams. So looking up there at zinc, 65.38 grams. And so we now have moles of zinc. We do the same thing now for phosphorus. So for phosphorus, we will have 20.3 grams multiplied by 1 mole of phosphorus. And looking at the periodic chart or the table at the end of the book, we find 30.97 grams for that. And oxygen, 36.8 multiplied by 1 mole of oxygen, again referring to its atomic mass, 16.00 grams. And so we now have everything in terms of a mole ratio. Well, let's go ahead and quickly calculate then this set of numbers. So we have 42.9 divided by 65.38. And the first one then gives us a value of 0.656. 20.3 divided by 30.97, we have a value of 0.655. And 36.8 divided by 16 gives us a value of 2.30. Now, once we reach this point, we now have a ratio expressed in terms of moles of atoms, but obviously it's not the smallest whole number. None of those are whole numbers. So the next step we take to guarantee that we have at least one in a whole number form is we're now going to divide each of the numbers we just calculated by the smallest number that we had. In the numbers that we have here, that means we're going to divide by 0.655, divide by 0.655, divide by 0.655. When we do so, obviously we're going to get 1 and 1 for the first two, and then dividing 2.3 by 0.655, we get 3.5. All right. Now, we have two of the three elements expressed as whole numbers. Obviously, the oxygen is not. And if we have a fractional amount, we have to begin looking for a multiplier. Now, I said that if we are within plus or minus a tenth, we can often round off. Only after we've made this division. We can't round off back here. We can only round off after we've done the division. Well, in this particular case, I think it's somewhat obvious that if we were to now multiply, so we're going to add one final step here, if we were to multiply each of these by 2, we will end up with whole numbers of 2, 2, and 7, and so the empirical formula for this compound would be Zn subscript 2, P subscript 2, O subscript 7, and that's the empirical formula of this compound containing zinc, phosphorus, and oxygen. All right? In the example we did in the previous lecture, after we made this division, we ended up with all even numbers. I believe the example we had, it came out 1, 1, and 2. Or 1.98, which we could round off justifiably to 2. But if it comes out something greater than a tenth, we'll have to look for a multiplier. Now, the things that we're going to most typically see as decimals out here would be something like 0.33. If we see that, what are we going to multiply by? We're going to multiply by a 3. To get to a whole number, a third times 3. Or we might see 0.25. This is this part right in here I'm talking about. If we got a 0.25, what would we probably use as our multiplier to get it to a whole number? 4. Okay. If we had 0.5, obviously we've already done that, is 2. If we have 0.66, what are we going to do? Multiply by 3. 2/3 times 3 would give us a 2. And let's see, the other common one might be 0.75. What could we multiply by to get to a whole number there? Back to 4, right, times 4. So those are the ones that we're likely to encounter in empirical formula calculations. All right, any question on any step of that particular one? Now, if we have calculated an empirical formula, and if we know the molar mass of the compound, we can calculate or we can determine the actual molecular formula. We can determine the actual chemical formula. Remember, the empirical formula may not be how the molecule actually exists. It's just the simplest whole number ratio of the elements. Now, how do we go about determining the molecular formula then if we have this information given? Well, the molecular formula is equal to the empirical formula multiplied by molar mass divided by empirical formula mass. And this will come out to be a whole number, or it has to come out to be a whole number. And again, we might do some small rounding off because of scientific measurements. So in this particular example problem that we're looking at here then, it asks us to calculate the molecular formula, problem 17a at the end of the chapter. And so we would say, all right, the molecular formula, the way the molecule actually is then, and I'm just going to abbreviate that MF, molecular formula would be equal to the empirical formula, CH2, multiplied by the molar mass, 70.15, divided by the empirical formula mass. So we have to calculate how much this weighs. Well, a carbon is 12, so let's see here, I have another problem. Well, I'll just do it down here towards the bottom. CH2, we'd have 12.01 for a carbon, and 2 hydrogens would be 2.02, 2 times 1.01, and so we have a 14.03 for the empirical mass. So we come back up here, 14.03. Now, 70.15 divided by 14.03 is equal to what? Well, we could plug it in on a calculator. It's equal to 5. And so our molecular formula then is CH2 multiplied by 5. Now, the 5 is used to multiply the exponents. So our final molecular formula is C5H10. So the actual molecule contains 5 carbons and 10 hydrogens. The empirical formula shows us a ratio of 1 to 2 carbon to hydrogen atoms. Obviously that is 5 to 10, but the actual molecule, the actual chemical we're looking at, then actually has a formula of C5H10, not CH2. To get to this point, however, one has to be able to experimentally determine the molar mass. And as we go on, we're going to look in a couple of chapters on how we can do this experimentally. In the gas law chapter, we're going to look at one method we can use. In the chapter on solutions, we're going to look at another method we can use. In laboratory work, we're going to look at a third method that we can use from the standpoint of acid-base reactions. So we're going to learn how we can do this part, but for now, all we can say is that if we have this given, and we have either the empirical formula or the information on the percent composition, we can in fact determine then the molecular formula. Problem number 19 then combines these two, and so we'll take a quick look at it. Gives us the chemical composition of the compound, gives us the molar mass of the compound, and asks us to determine the molecular formula. To do so, we must first determine the empirical formula. So, we're going to do this just like we did in the previous one. We're going to start with carbon. We have 85.60 multiplied by 1 mole of carbon over 12.01 grams. So the grams cancel. Then hydrogen, 14.40 grams times 1 mole of hydrogen over 1.01 grams. And we mathematically then need to determine this. So we have 85.6 divided by 12.01. And the first one I get there, 7.127. And we have 14.4 divided by 1.01. And we get 14.25. If we divide each by the smallest, excuse me, if we divide each by the smallest that we obtained, so this is our second step, we get a 1 and a 2. And so our empirical formula for this compound is the same as what we saw in 17A. The empirical formula is equal to CH2. Now, to determine the molecular formula then, we are going to have to use the molar mass and the empirical formula and the empirical formula mass. In this case, it just happens we already have it calculated because it's the same empirical formula as the one in 17A. So, the molecular formula is equal to CH2 multiplied by our molar mass up there, 42.1, divided by the empirical mass, 14.03. That is equal to CH2 times 3. So the molecular formula is in fact C3H6. Now notice, problem 17A, we had an empirical formula CH2. Problem number 19, we have an empirical formula of CH2. But they're not the same chemical compounds, even though they both had a 1:2 carbon to hydrogen ratio. The actual compound, we have to know the molar mass to get to that point. These two compounds, C5H10 and C3H6, are two totally different chemical compounds. Two different organic compounds, that we refer to as hydrocarbons, organic compounds that contain hydrogen and carbon only, are called hydrocarbons. These are two different hydrocarbons, two different organic compounds. All right, any questions on any step of that? Well, then I'd like to spend the remainder of this lecture going back and picking up a little bit at the earlier part of the chapter, as I mentioned when we were talking about two types of formulas. We talked about, first of all, the chemical formula. And then we talked about the structural formula. And the structural formula tells us how the atoms are hooked together. The chemical formula tells us how many of each type of atom are present. That's all it tells us. And if you look back in the first lecture in this chapter, you'll see that we looked at a couple of compounds, sulfuric acid. We showed its chemical formula and its structural formula, phosphorus pentachloride, PCl5. We showed a chemical formula and a structural formula. Where we're going to apply this today is in the area of chemistry that we refer to as organic chemistry. And organic chemistry is the chemistry that is based essentially on carbon. Carbon as the backbone of all of the compounds that fall in this category called organic chemistry. And one of the first groups of organic chemical compounds that we're going to look at are the ones that I just mentioned, called the hydrocarbons. And the hydrocarbons contain only two elements, hydrogen and carbon. Now, there are many different hydrocarbons that we have, and we're going to look at, in this particular chapter, first of all, we're going to look at the simplest, I guess I would call it the simplest group of hydrocarbons, which are referred to as saturated hydrocarbons. Saturated hydrocarbons means that we have the maximum carbon-hydrogen ratio that there is in any organic compound. That's what is called a saturated hydrocarbon. They will all have a chemical formula of CN, where N is any number that we want to plug in, H2N, that means 2 times whatever number we used for the carbon, plus 2. They will all have that carbon-hydrogen ratio. In other words, if I have a saturated hydrocarbon which has 6 carbons, then it would tell me that to be a saturated hydrocarbon it would need to have twice that many. 2 times 6 would be 12, plus the 2. So the chemical formula for a saturated hydrocarbon with 6 carbons would be CH14. Okay? All saturated hydrocarbons fit this chemical formula right here, this general formula, C6H14. These also are sometimes referred to as the alkane, A-N-E, and I'll come back and mention this A-N-E aspect just a little bit here in a moment. These are called the alkanes as a group in organic chemistry. And what we're going to try to do as we go along in the different chapters is we're going to try to look at some different organic chemical groups of compounds that fall into this area called organic chemistry. Organic chemistry is probably the biggest individual subgroup of chemistry that we have. We are probably most involved and impacted by organic type chemical compounds. The fuel in your automobile, the rubber making up the tires, the plastic, the clothing that you're wearing, much of the food that we eat are in this category of organic chemicals. And so we're going to look at some key categories, some key groups of organic compounds as we go along. Not so much to try to memorize all of them in terms of chemical formulas and names and all of that, but to have a basic understanding of this major area of chemistry called organic chemistry. Now, Table 2.1 in the text lists 10 of the alkane hydrocarbons. All of these have that CnH2n plus 2 relationship. And we want to just take a look at a few of these because these are compounds that we do encounter on a rather regular or routine basis. And so let's take a look, and I would like you to, at least in this case, know the names of these and their chemical formula. Now that might seem quite difficult at first, but when we point out a few things here, I think you'll see it's not that much of a problem. The first 4 that we have up here, methane, CH4, that's the simplest hydrocarbon. Methane is the major constituent of natural gas. If you have a natural gas furnace in your home, it's heated by that. The major component of the gas that is being burned in that furnace is CH4, methane gas. So natural gas, or actually the name methane, probably arrived from its early name, which was called marsh gas. When marshes undergo decay, the biomass begins decaying, one of the products that we have from that decay is methane, or natural gas. Another component of natural gas, but in a much lesser amount. This is usually probably in the range of about 90% of natural gas. About 10% is the second one, called ethane. And we won't worry too much about ethane right now, but we will come back and talk about its chemical importance in future chapters, because as it says, it's a starting material for a chemical compound called ethene. And when we talk about ethene, we'll see its commercial importance. It's a very, very important industrial chemical. But the next two are two that you're probably familiar with. C3H8, propane. If you go camping, you probably take along some sort of a cook stove that operates on propane. This LPG, liquid petroleum gas. LPG is liquefied propane. If you have a grill in the back of your home or something and have a tank on it, that's propane. If you live in a rural area and don't have access to natural gas, you are probably heating your home with propane. The large tank, they bring it out as a liquid and put it in the tank. Liquid propane. The next one, butane, is the gas, is the hydrocarbon we find in cigarette lighters. Butane cigarette lighter is then using butane for its fuel. And butane at room temperature and a small amount of pressure is a liquid. It can be liquefied relatively easily. Now, the next six, if you look at their names, and this is what makes it easy to remember them, look at their names. Pentane. What's the prefix for 5? Penta. Hexane. What's the prefix for 6? Hexa. Each of these compounds then from C4 on, starting with C5, are named using the prefix system. Pentane, hexane for 6, heptane for 7, octane, and I'm sure you've all heard that one, means 8 carbons. So when you see an octane rating on a fuel pump, what they're talking about is that this fuel is compared to a particular sample of gasoline that is rated at 100. And so if you then buy gasoline that says 87 octane, it means it has the burning rate, the power rate of about 87% of what the pure isooctane used as a reference would be. All right? Nonane, and then finally decane. And you can see that a lot of these are components of gasoline. Okay, so gasoline is a mixture. As we pointed out in Chapter 1, it's not a compound, it's a mixture of many different chemical compounds. Now, one of the things about organic compounds and structural formulas, let's take a look at C5H12 for a second. That's the chemical formula, C5H12. Now, structural formula-wise, I could hook the 5 carbons together and I could put hydrogens on. We'll find in a later chapter on chemical bonding that carbon has the ability to form 4 chemical bonds. And what we'll see here is that each carbon in this structural formula has 4 dashes, 4 chemical bonds associated with it. We will later find out hydrogen can have only 1 chemical bond, and so we see that each hydrogen is hooked to a carbon, but we couldn't have a hydrogen hooked to a carbon hooked to another hydrogen. That is not a possibility for hydrogen to do. It can only form 1 chemical bond. And if it's used it to hook to the carbon, then obviously it can't hook to something else. Now that's one way that I can hook these together. But in organic chemistry, it turns out that many of the chemical formulas can be shown in many different structural forms. For instance, I can take this same one, I will put 4 in a row like this, and I'll branch one off this way. If I hook the hydrogens, remember I can only have 4 dashes on each carbon here, as I just said. So if we do this and put the hydrogens on there, and we count up the hydrogens, we'll find that we have 12 hydrogens. That's a unique molecule. That's the same chemical formula, but it's a totally new structural formula. It has different boiling points. It has different chemical reactivity. It is a different chemical compound. Even though it has the same chemical formula, it in fact is not the same chemical compound. Well, as a matter of fact, let's see, we could maybe do something like this. We could put 3 in a row, and we could put a couple of carbons off the middle like that, and then we can put hydrogens around here. I won't bother to draw each dash this time, keeping in mind that each hydrogen has 1 dash to the carbons. And that is a third way that we can hook 5 carbons and 12 hydrogens together to make the same chemical formula, C5H12. Again, each of these is a unique chemical compound. Each of these has a different chemical name. Okay? This one, as the chart showed us, would be called pentane. This one, however, and you don't need to write these down, but I'm just pointing out we do have a naming system. This one is called methyl butane. And this one is called it's called 2,2-dimethylpropane. They have different chemical names for the 3 different structural formulas, even though they are the same chemical formula. Now, in nature, when we have more than one way to hook the same number of atoms together, we refer to these different types of structures as isomers. Isomers, term that you need to remember. And when these isomers are, because of the different structures we have drawn, we specifically call them then structural isomers. Now, what a structural isomer is, once again, it is a chemical or 2 different forms of the same chemical formula hooked together in a different fashion. We have to obey the bonding ability of the different elements when we do this. We can't just hook things together and make arbitrary new structural formulas. They do have to fit some sort of bonding criteria. Yes, a question. The question is, should the one in the middle be named 2-methylbutane? That's a very good question. And the answer is, it could be, but it's not necessary. The only place I could put a methyl group, methyl group is this little CH3 that we have hanging here. The only place that it could be put would be on the second carbon. If I put it on the end, I would have 5, and I would be back to pentane. In this case, I can only put it there. If I put it on this one, remember, I drew the molecule. The molecule doesn't know left from right. If I stood behind the board and looked at it, it would look the reverse way, but that's not a unique molecule. Now, if there is any question in our naming, we could certainly use the term 2-methylbutane, and that's certainly a good answer for, or good name for it. In this particular case, as I say, because we're not really concerned at this point of trying to learn the organic nomenclature, but to look at different groups of organic compounds, we won't worry about each little individual criteria that we need in the naming. But yes, it could be called 2-methylbutane. We could call it just methylbutane. we would have to draw exactly the same structure regardless of what the name was. So the more information we put, of course, the clearer it is to someone. But also in chemistry, we often try to write things in the simplest fashion we can to still get across the information that we need. All right, so structural isomers. So we have chemical formula. We have a structural formula that shows how things can be hooked together. And then we see that in some cases we can hook things together, the same chemical formula, in more than one way, which gives us then what we call structural isomers. All right? Now, just to give you some idea of the magnitude of this, if we go to the C8 compound, I believe we will have 18 different isomers that we can have. If we go to C9 with the correct number of hydrogens, we'll have something like 35, and when we go to C10 we have something approximately 70. So you see the number of different isomers one can have for the same chemical formula becomes very, very large. And we have many compounds in hydrocarbons that are 12 to 25 carbons in them. So many different ways that we can write them. In our next lecture, we'll take a little bit of a quick look at how hydrocarbons are obtained and processed then for our use. Okay?